We got Avimila, who works from Oracle, and he said to me his bio is very boring, so I'm not going to read it for you. And so, Avi, just...
Thank you. Okay, I am from Oracle, don't judge me. Don't beat me. But if you'd like a job, we are hiring kernel and other developers, and we have cookies and stuff. So if you do want to work on the kernel, you want to work on mainline features, we do have quite a large mainline kernel development team that has absolutely nothing to do with Oracle products, you'll be glad to know. They're completely isolated from product development. So if you just want to get paid to hack on the kernel, let me know. First up, I'm not the guy who was scheduled to do this talk originally. The original developer of Transcendent Memory, Dan Magenheimer from Oracle, was scheduled and approved to do this talk, but unfortunately personal circumstances mean he couldn't leave the US at the moment. He's got some stuff on. So he asked me if I would do the talk for him, and like a fool, I said yes. But if you saw my talk last year I decided to do a file system talk at LCA. This year I'm doing kernel memory management at LCA, and I don't do any kernel development. I'm a principal program manager for Oracle Linux, which means that I'm responsible for product management and release management of various bits of the Oracle Linux product. Of that, Transcendent Memory actually does fall into my product stack, and I have used it for about 4 years. And I was the original guinea pig upon which the first sort of pre-releases, prior to even thinking about merging, would happen of Transcendent Memory, so I have some history on it. I'm going to be calling it TMEM from now on, because Transcendent Memory is way too many syllables for the time I have. So I will be calling it TMEM. Anybody here in the keynote this morning? Anybody here did not know what an FPGA was before this morning? Because I had to Wikipedia it this morning. It's a field gate programmable array, by the way. You can thank me later for that. If there is a term you don't understand in the middle of my talk, just stop me instead of Wikipediaing it, and I will stop and try and explain that one. There are a bunch of terms that I'm going to throw at you during this. Some of them we made up as part of the TMEM environment. Some of them exist inside the kernel already. If you want further discussions, further reading, Dan's original article on Transcendent Memory is called Transcendent Memory in a Nutshell. It is on LWN. The slide deck will go out later, so you don't have to take pictures of it and stuff like that. It'll go up into SlideShare, and the organizers will send it out, so you'll have the URLs. At the back end of the presentation, once I get to the pretty graphs and stuff, there are death by wall of text slides. So when you first see them, don't get frightened. I'm not going to read them at you. They're there, so when you get the slide deck, you have a reference for some of that information later. So the objective for Transcendent Memory was to utilize RAM more effectively. Now, anybody here run virtual environments? Okay. Anybody here run proprietary virtual environments? Anybody here ever turned on their memory management functionality in that virtual environment? Anybody here then turn off that memory management functionality? And there is a reason for that. Memory management done without the knowledge and understanding of what they're managing is tough, and it takes lots and lots and lots of CPU cycles. So if you turn on memory deduplication, you turn on memory compression, you turn on memory overcommit, you waste CPU cycles at the cost of a little bit more memory. So our goals with Transcendent Memory and TMEM were to lower our capital costs, yes?
When you're talking about memory overcommit, are you talking with or without KSM on Linux?
I'm talking without.
Okay.
So our options here: lower capital costs, lower the power utilization, less I/O, and improve the performance of our workloads. And they seem, when you look at memory overcommit, that is the contradiction. How do you do memory tricks without impacting your workload performance? So historically, we have plenty of memory inefficient workloads. What used to happen is we would lovingly virtualize because CPUs were sitting all idle on individual boxes. So we figured, hey, what we can do is we can shove all of these machines into one big box. And then we found that the problem wasn't actually the fact that we were undercommitted on CPU, the fact that we were bottlenecked on RAM anyway. And once we got into this really big box and vendors had sold us on the fact that, no, you don't need to fill it up with memory, what you can do is turn on this button and then it's going to do all sorts of fun memory things, and then we discovered that all that spare CPU cycles that we thought we had, we no longer have, and we turned all that stuff off. The other problem is we have a capacity wall now. So if we look at how many cores our machines have, it's growing fairly interesting, and we're sitting at about, because we're 2012, if you'd like to, you can buy Sun Oracle boxes that now have 12 cores per socket, 24 threads, and have 8 sockets per machine. So you can buy a machine that's got 80 threads, 80 cores, 96 cores, 160 threads, 192 threads if you like. But the total memory capacity in those machines is not increasing as quickly. So we're starting to see almost a 30% capacity per core drop. So the amount of memory you can shove in a machine is not growing as much as the amount of cores that we can shove in a machine. So that gives us spare CPU cycles, by the way. Less memory, more cycles. Power, that's Google's data center in Belgium. Very nice. The contribution of memory to the total cost and power consumption is increasing from its current value around 25%. So that old thing, we'll just shove more memory into the machine. It's a great option if you have spare slots in the machine, but you start paying more for the power to those machines. And Google does some anybody here from Google? I'd love a site tour eventually, just saying that. Putting it out there into the world. I've read The Secret. If I say it enough times, maybe it'll happen. But you guys don't use normal power. You have all sorts of fun DC power that goes, they've built their own things. They've got low power servers that go into the stuff, because they've got billions of them. It's a fact, you can take that. And we're changing what memory looks like. And back in the day, we had a core, we had some DRAM, we had some disk, and we had tape. Now we've got multi-core disks, multi-core processors, we've got DRAM, we've got flash, we've got lots of disks. Now, we're looking at many cores. We've got 10 core, 12 core. Anybody here run Spark boxes? You can get 32 core Sparks now. You've got machines that have got 32 cores on a single socket. We have DRAM, we have NVRAM, we have flash, we have disks and tape. So we have lots of new technology that has idiosyncrasies. Things like write cycle issues that won't take, they're as fast or almost as fast as RAM, but they won't take the load of being used randomly, if that makes sense. We have disaggregation. We have blade chassis and we have exofabrics, which are really cool ways of saying external to the blade chassis. Anybody here work at BOM, Bureau of Met, down in Melbourne? If you ever get a chance, if anybody ever introduces you to somebody who is a techie at the Bureau of Met and they can get you into their computer room, take the option. Because they're HPC, it happens to be a Sun Oracle cluster, which is why I got to see it. But it is the most amazing example of the most beautiful cabling job I've ever seen in my life, in the sense that every single network cable is in its own tray, out of every switch, because everything is InfiniBand. And so out of every blade chassis are these InfiniBand fans, and every cable is exactly the right length to sit in every single tray, and it is remarkable. But they have really interesting stuff. They've got memory blades. And they can disaggregate memory into a separate machine. And that doesn't actually have to be DRAM, as we'll see a little bit later. The memory blade doesn't actually have to have memory in it, which is quite fun. When we're talking about exofabric, essentially anything that uses kernel sockets, it does work over gigabit Ethernet, and the examples that I'll show you later is on gigabit Ethernet, but it's more designed around 10 gig Ethernet or InfiniBand, 40 gigabit InfiniBand. Anybody here running InfiniBand? Oh, isn't it fun? Okay, so the biggest problem, however, with playing with memory is that operating systems are memory hogs. So if you have a memory constraint, and usually at this point it's physical memory, you've got 8 gigs of RAM in your machine, let's say you've got 4 gigs of RAM in your machine, and then you go and add another 4 gigs of RAM to your machine. Anybody want to guess what the operating system is going to do? It's going to use up every little bit of memory you can give it. I'm Linux and I'm a memory hog. And it does this on purpose. Okay? It does this because memory is the fastest thing it can access on its bus for storage purposes. Okay? So, in the realm of performance, if I can get stuff out of memory, it means that I don't have to go to disk. And if I'm a blade, that means I may not have to go to shared storage. And if I'm using shared storage, I may not have to go to network file systems as opposed to fiber channel and all that kind of stuff. So the more that I can do locally, the faster it is. In a virtual environment, however, this is quite a challenge. Because guessing how much memory your VMs need at any one time is an arcane black art, and ballooning becomes very difficult unless you have knowledge of what's going on inside the guest. If something happens low, so what we really need to do, the first thing that we had to do to get Transcendent memory to work is put Linux on a diet. Now, all of this, by the way, is all mainline Linux stuff. It is potentially portable to other operating systems, but nobody's even thought about that at the moment. But what we're thinking at the moment is, as opposed to the historic premise, let's use all the memory that you're given to us, we're going to reverse it. Let's use as little memory as possible. Memory asceticism, extreme self-denial. Okay. Suppose we give the OS a mechanism by which it can surrender memory. And we give the mechanism to the OS by which it can obtain more memory. That's quite an interesting one. Therefore, we're giving the guest, the thing that knows what it's using, the ability to say, okay, I don't actually need all of this stuff. And then when it does need this stuff, it gets it back. Okay. How much memory does an OS need? Anybody got a piece of string? It's about that long. But we can actually find out. There's quite an interesting way of going through this. I'll take you through a thought experiment with pictures. Okay. So there you go. Cutting edge memory chips. Can you see? Nothing but this. Anybody here ever used the original sound blasters? Remember those days? Anybody ever put the FM synthesizer modules on those? I broke 4 of them. But they look, you bought your original Sound Blaster and it didn't have FM synthesis and you could buy the chip separate. Oh, it was so cutting edge. It was the last time I ever did any hardware work. I thought, no, after that. Okay, so assume your computer has an amount of memory. What we want to do is we want to split that memory into 2 parts. Okay? And for ease of use at the moment, I'm going to call them Type A and Type B. I'm going to put Type B memory behind a curtain. The reason for that is that Type B memory is dynamic. I can slide the curtain backwards and forwards. I can increase and decrease the amount of memory in Type B. Okay. So as I move the curtain, the amount of Type B memory is going to change. So Type A memory, we're going to keep it as a known capacity. The processor and the operating system can read and write and address any byte of that memory. It is normal operating system OS memory. Okay? Type B memory, its capacity is unknown and it may change dynamically at any time. Okay. The problem with this, okay, so first of all, the best thing about Type A memory, we know the capacity, we use it for all the normal stuff, direct memory access, user and kernel memory, we can address, read and write any byte. It's all normal RAM. Type B memory, unknowable, cannot be addressed directly. That's a challenge. Okay, so this memory becomes unaddressable. We need to teach the kernel how to put memory in, get memory out, and follow the rules. So usually a kernel is all about ego. It's all about I will do whatever I want with the memory that I have. Now we're teaching the kernel to be slightly more polite. The rules. These are the rules. The first rule of transcendent memory. Don't talk about that. First rule, page at a time. By default, the page is 4K, but we support huge pages as long as the page size never changes. Okay, so you can do huge page transcendent memory. This becomes really interesting a little bit later when we see what type B memory actually is, but it's a page at a time. To put data in type B memory, the kernel must use a put page call. Okay, makes sense. So, here is a lovely page of memory, and I'm going to put it into type B memory. Let's call the page tux. There you go. We have a page that contains tux, and the kernel wants to preserve tux in type B. So, the kernel asks for permission and may get told no. That's the fun bit. Anybody want to guess why?
Might not be memory available.
There might not be any memory available. We don't know how much type B memory is there. Okay, so we do a put request, we may get told nah. Okay, so we have two options to that put request. We have, I'm going to put tux into type B memory, and I definitely want him back, i.e. a dirty page. Anybody, you might see where I'm going with this one. Okay. Or I want to put tux into type B memory, and I probably want him back, i.e. a clean page. Okay, if he disappears. So in the first option, definitely want tux back, or I probably want tux back. Type B memory, you may have guessed, is transcendent memory. It's beyond the range of normal perception. Oddly creative for a kernel developer, I thought. His naming is quite good. I've got a thesaurus out for this and everything. Okay. So type B memory is transcendent memory. The two options when we're putting is a persistent put and an ephemeral put. Okay. I definitely want tux back, which is a dirty put. I probably want tux back, which is a clean put, persistent and ephemeral. Okay, so those are my options. We have a third command, which is a flush, which is when the kernel tells type B or transcendent memory, I don't actually need that anymore. Okay. Now, by the way, if you can find whoever owns the copyright for that image, let me know. I did lots and lots of searching and then decided to use the image anyway because it was so cute. I know the rest of them are all Creative Commons and allow commercial use, so I went with that, but this one is too cute not to use. Okay. So, how do we identify the pages that we want to put, get, or flush? So, normal RAM is byte addressable. It has a virtual address space. Processors have been doing this and kernels have been doing this for years. There's nothing miraculous about this. Can't do that with transcendent memory. Transcendent memory has object-oriented addressing. So every page is an object, every object is a page. There is a handle associated with every page that goes into transcendent memory. We use the same handle to get, and we must ensure the handle is and remains unique. And this one becomes really fun when we take a look at what happens later with transcendent memory. Keep that in mind. Not just is, but remains unique. Okay. Why bother? Because once we're behind the curtain, we can do really interesting things. Okay. So the first interesting thing, and this is where transcendent memory actually started. Dan, who wrote transcendent memory, wrote TMM support into Zen back in the days of 4.0, so 2009, 3 years ago. Virtual machines that are guests of a Zen hypervisor that are TMM enabled, instead of using all the memory you give them, can self-balloon. So they will release their entire page cache back to the Zen hypervisor, which then contains a pool, both a persistent pool and an ephemeral pool. So the Zen hypervisor can then support multiple guests. It can do compression. You give me a clean page of what would be a page cache page in a normal bare metal machine. You give it to me as an ephemeral put. I don't really need it back, but it'd be nice. I compress it because most data compresses 2 to 1. Most, a lot. I can do deduplication. Intelligent deduplication. Why? Because I have the handles. And if I've got 2 OSs, identical kernels, and they both try to do a put with the same handle, because it has to remain unique, then Zen knows that they're putting the same page of memory. If you boot 2 kernels that are identical, a lot of the kernel is the same. So I do intelligent deduplication of memory at the hypervisor level, which is quite fun. This works, by the way, so I will flip out and for those of you who haven't seen Oracle VM, you might not still. Let's go and connection refused. Why? Oh, because I'm already on my VPN. No, I need to be root. Those who... Okay. What I'll do is that is a tmem pause. More difficult to see. 5 to less minus capital S. There you go. What we can see is 2 domains that are running. Domain ID 18 and domain ID 19. Inside here, there, you can see successful ephemeral gets. Down lower is persistent puts, that kind of, yeah, puts some, there's some domain 19 puts here as well. There are various compression cycles, decompression cycles, page copy cycles. It's all very fun. So this is Oracle VM 3.2. It has been working from Oracle VM 2.2. I'm doing it, happen to be testing Oracle VM 3.2. Running Zen 4.1, I think. Essentially, I've got tmem enabled on this server with all the options. Tmem's enabled, compression's enabled, which uses the Zcache engine, which is zlib compression. And the dedupe is enabled as well. So there's deduplication cycles happening somewhere as well. Which is quite fun. But the Zen top, basically, if I did that, will show you your tmem ephemeral gets, ephemeral puts, current ephemeral pages. There's successful puts, successful persistent gets, that kind of stuff. So you can see how busy your tmem is. Okie dokie. So that's where, ooh, come on. There we go. That's where we started with Transcendent Memory. The idea was we had a virtualization product and we wanted to offer memory overcommit, but we wanted to do it in a way that didn't impact performance. The second thing you can do, and this works in any Linux, you can just compress. Turn on Zcache. So now you compress on your put and you decompress on your get. Because compression is a couple of CPUs. At a cost of CPU cycles, yes, because you're compressing data, but your memory utilization becomes that much less. Okay? Most data compressors with about a factor of 2, so you could potentially save a lot of RAM. If you can't put more memory into a physical machine, and you can't move this application somewhere else, you could better use the memory you already have by compressing your dirty pages and your clean pages. You can do something else. You can transparently move pre-compressed pages across a high-speed coherent interconnect. So now, instead of if I don't have enough memory in one machine, I can go and put it in memory in another machine. Because we have interconnects between machines that are faster than spinning disks. Okay. The ability to get data across a network, particularly 10 gig Ethernet and InfiniBand, is faster than a spinning disk. And it's certainly faster than fiber channel. That's called Ramster, named after the poorly and short-lived Napster. It's peer-to-peer transcendent memory. There is a cluster engine inside the kernel. It's called O2CB. It's part of OCFS. And it's a really nice cluster heartbeat. It allows lots of peers to communicate with each other. We're not doing storage, we're doing peer-to-peer stuff. This is not shared memory, though you can do it client-server. This is the ability for one machine to start talking to lots of machines, and we already have a distributed locking mechanism for that memory, and we have a way of sending stuff around. So we pretty much just reuse the OTCB code. We have, by the way, because this is in Linux staging, split it. We're not using the original OTCB code, we're using a copy of it just for Ramster for testing purposes. The goal is eventually to merge them back so we only have one set of O2CB. We can do another interesting thing, we can do SSMem. Transcendent memory is a safe way of using SSDs or NVRAM. Instead of trying to use those as random access devices, we can use them as I/O devices and then have a transcendent memory backend reading and writing from your very memory-like I/O device.
Node-to-node communication.
Yes?
Why does it necessarily have to be in kernel if you're...
It doesn't. It doesn't necessarily have to be in kernel.
Why not use Corsync?
Write it for us.
Well, Corsync is there.
No, write the connection to, write the backend for transcendent memory for Corsync. Go nuts. It's there. And you'll see a little bit later that that's one of the designs is that there is no fixed way to do type B. We have clients and backends for transcendent memory. I'm getting a bit ahead of myself, but you can just swap out the backend. Combine those two. Ramster plus SSMem means that you have a one large memory server that's shared by lots of machines that doesn't actually have any memory in it. It just has an array of SSDs, okay, or array of NVRAM. Because one of the interesting things, I was asked this question on Tuesday or Wednesday, I think. If you put a persistent put into another machine, this is something that you have to get back. It's a dirty page. How do you ensure that you do if it's going to another machine? Well, you write it to something that's permanent. You don't rely on volatile memory. You put it into non-volatile memory. And then you do lots of things that you replicate it and stuff like that. So, most of this stuff is already implemented. Some of it is not. Some of it's in very experimental stages. We've got a few of the stuff already. We have clean cache. Okay. So clean cache is in kernel, was merged back in the 3.0 days. It's a third level victim cache. So when clean cache is enabled, config_clean cache equals yes. What the system will do is when it has to put clean pages, it will attempt to put them into a tmem backend if one has registered. If not, it's a no-op. So if no tmem backend registers on a machine when it boots, then the clean cache and the front swap, which is next, become no-ops. There's no performance impact. Per file system opt-in hooks, we have them and we've written them for X3, X4, ButterFS, and I believe OCFS too. I'd have to double check. There is a shim to Zcache that came out in 2.639. There's a shim to Zen tmem in 3.0, which means that for clean pages, what we can do is we can compress them, or we can send them down into the hypervisor tmem pool. There is front swap. Oh, really? Wow. Okay. To swap, these are dirty pages. So it's a swap subsystem exactly the same as clean cache. You enable it with config front swap. If there is no backend, there's no impact. Okay. So, tiny little core changes for clean cache and front swap. The backends, there are no core kernel changes for them. They're all implemented as drivers. So you can swap them out. So that's where they sit. Zcache and the replacement, which is Zcache 2, came in 2.639 and 7.3. Ramster was merged with Zcache 2 in the 3.7, so there's a single 1.9 staging. Front swap and clean cache, Linus actually decided to put them in. There was a long, those of you who do subscribe to LKML, first of all, sorry. Second of all, long discussion on that stuff. All the self-ballooning and self-shrinking happens with that kind of stuff. Lots of things happen. Unfortunately, I have to do at least one corporate slide. We have Transcendent memory now in upstream, clean cache, one swap, guest kernel support for Zen, Zcache and Ramster are in. Transcendent memory has been in the Zen hypervisor and it's been available in Oracle VM, the product, the actual server product, since 2.2. It's been in our UEK2, which is a 3.0 kernel for Oracle Linux 5 and Oracle Linux 6 for about a year now. Okay. It is not, however, in our management product. So you can turn it on like I did, but our management product is not aware of Transcendent memory, therefore it only ever sees and it thinks that the guest has used as much memory as it starts with. So on the roadmap is to get our Oracle VM management products to do TMM querying when they start and stop guests to see what the current state of memory on a hypervisor is. So pretty graphs, facts and figures. Why do we do this? So this is a performance analysis of the Zcache and Ramster add-ons. Now, if we look at front swap, for example, it's less than 100 lines changed. Okay, there's no impact if you don't configure it. There's negligible impact because it's a no-op if there's no backend. So let's turn on a backend. We're going to turn on Zcache first. These are stats. You will get them when the slides come out. I'm not going to go through them, but the upshot is we did a make of the kernel with a -jn, and essentially what we wanted to do is force memory pressure. So on a small n, there's no memory pressure, there's a medium, there's a large, and there's a largest. So all we're doing is basically pressurizing memory. It's a fake workload to force memory pressure onto the box. And this is a Dell workstation. It's a $500 machine. So if anybody has lots of hardware that they want to give us to test, that'd be great. So this is what happens on that machine. Down at the low end, it compiles. It's quite good. Up at the top end, once we start getting lots of memory pressure, we start getting lots of caching, lots of swapping, and eventually once you do 40 threads on a tiny little quad-core machine, it doesn't finish. Okay, it eventually just dies. So the upshot is, okay, let's turn on Zcache. Zcache is going to compress things as they're put. It's going to decompress things as they're get. We're going to save one disk access for every get, and disk write and read for every get as well. Again, you can review these later. That's what happens. Down at the low end, negligible sort of changes. But once we get memory pressure, once we're doing some, and I'll show you, if we go back a couple of slides, what happens with the memory pressure that we set. The large, lots of page cache churning. Okay, lots of swapping. Once we get to that point, the compression, we're seeing a 25 to 30% increase in performance because the compression cycles means we have to do less reading and writing from memory. We're doing it in smaller chunks. There's more CPU cycles, but that's fine. We actually have them to spare in this. We don't have the spare memory at this point. And at the top end, we actually finish at very heavy memory pressure. It's not an effective finish, but we do finish. Okay. So under no to moderate memory pressure, we increase the total pages cached due to compression, a moderate performance improvement, 10 to 15%. But at high memory pressure, we're improving 25 to 30% because we're doing compressed swap. We're not swapping to disk. We're saving those disks reads and writes because we have more memory, and we're increasing the total pages cached. And we eventually finish because we reduce the swap storm at the bottom. Now let's add Ramster. This is using memory on a different machine. Okay, RAM management is entire dynamic. We had one node doing the compression. We had 8 nodes, up to 8 nodes. Now, before you ask, I don't know how many nodes were used in this test, and I don't know how much memory they had dedicated to TMM. I had emailed Dan and asked him the question because that occurred to me last night when I was reviewing it. But as I said, he's off on personal stuff, so I don't know when he'll get back to me. If it's very important for you to know this, ping me and I will find out and tell you. But that's what happens next. Okay. Once we add Ramster to the box, down at the nice big, we're still seeing the same sort of stuff. Now we're dropping even further, and that's really interesting. Okay. Okay, significant drop at the very high memory pressures. Because now we get a much bigger memory pool to play with. And this is over 10 gig, single gig, 1 gig Ethernet. This is not even over serious networking. This is, I'm going to guess, Realtek network cards. Okay, because I know what we put in our Dells. So, yeah. Its local compression happens first, somewhat slower than Zcash, but performance, it's, again, at the low end, we've got compression, but we have that network traffic. So it's slightly slower than just Zcash. Here we've got remote RAM to avoid the swap to disk. A 7200 RPM SATA single disk in a Dell is a lot slower than gigabit Ethernet to somebody else's memory, by the way. Performance improving 20-odd% on very high, and remote RAM significantly reducing the swap stall. That's why we're doing this. So, there we go. Those are my pretty graphs, those are my pretty pictures. I have about 3 minutes. Questions? Oh. You have to use the microphone. Florian got into it. Okay.
Which bits of the kernel are actually benefiting from it? Is it everything, or is it just selected parts?
Well, no. I mean, everything, no. Clean cache, so clean pages, so the page cache, yes. And dirty pages, which is swap. So that's, we front swap and clean cache are hooks to the page cache and the swap interface. And they are the majority of memory usage in the kernel. It's quite fun.
Is someone actively working on Transcendent memory support for KVM?
Yes, they are. There are some Red Hat guys who are working on, there is a testing driver for KVM that does Transcendent memory, but I don't know what the status of it is. I saw some, in fact, when the arguments on heated discussions on LKML were happening, about whether front swap and clean cache should be merged, and the Zen guy said we really want it, and the mainline guy said but Zen's not in mainline yet. That's where it all started. The KVM guy said but we are and we want it too. So yes, there is work from KVM on that, but I don't know where it is, so you'll have to check. There was a question at the top there.
Would it be reasonable to describe this like the kernel having a heap?
Having
a heap to allocate from?
Yes and no, because it's more than that, because the kernel can get told no. So essentially it's what we call a third victim cache, in the sense that the attempt to go to memory will be tried first because it's faster, but the response might be nah. So it's not guaranteed. There's no guarantee, and with an ephemeral put to Transcendent memory, there's no guarantee you'll get it back. So it's more of a case of CPU cycles on a lot of machines are cheaper. The memory wall means that we have more CPUs than we do RAM that we can stack up, which means let's use some of that spare cycle, particularly on virtual servers, where you tend to overspec your CPUs, because you can. Let's use that and maximize the amount of memory we can get out of the box.
The LWN article that you mentioned at the very beginning
yes.
is from 2011, and there it says that there is currently no clean way to use TMEM from user space, which might sort of be interesting for applications that otherwise typically circumvent the page cache, as most database workloads have to do. Has that changed anyway, or is that still? No,
it hasn't changed because our focus on it didn't need it to change. In the sense that our focus in the development of Transcendent memory was clean cache and front swap. And the biggest consumption of spare memory, and I use that slightly incorrectly, but Linux is a memory hog. The memory that it's hogging, it's just assigning to page caching. So the ability to do clean cache and move all that page caching elsewhere was the first focus. Swapping was the second, and that's pretty much all we want to do. The database guys have turned around and said, there's no way we're doing that with anything else. You can do that with your OS, that's great, and it works. And we have our products running on Transcendent memory enabled guests, and it's phenomenally fast. But we wouldn't do that into our product stack. And they do other things. They have cache fusion and other things inside the product stacks that do similar things with rack nodes and WebLogic clusters and stuff, that they're doing their own object replication and stuff. Shared PGAs and shared SGAs and stuff. Yep.
I think it's fair to say that with the large enterprise databases, they've had so little confidence in the policies in the operating system that they tend to say, just give us a bunch of memory, we'll work all this out on a user space basis between our client peers on other nodes, and then just sort it all out, just like you used to give them raw devices and all the rest.
Yeah. And you know, if I use our own product as an example, if you look at Rack, which is real application clusters, check it out. Cache fusion and the SGAs and stuff are all mirrored and replicated between rack nodes and stuff like that. And they handle all of their very involved memory handling between themselves at a level that makes sense for the database. And this is a level that makes sense for the operating system and potentially a hypervisor. And it's really putting that smarts at the level that makes the most sense.
So this might be a slightly dumb question, but what happens if you've got TMM set up, and you've got a bunch of VMs, they're all running, and you've got your blade storage for your memory? What happens when the cleaner unplugs that and it goes down? Do all your VMs go?
Potentially, yes. That's why the client-server model of RAMs, if you put RAMs to shared memory or a blade server as a concept, you wouldn't do client-server with a single box that's not using non-volatile memory. So as a memory server, you want to use SSMem in that instance, where if that machine gets unplugged, the memory that you've got from other machines is actually stored on SSDs or NVRAM. So when you plug it back in, the memory comes back. If you're doing it to volatile memory, you want to do it as peers, where you've got multiple copies of that memory. And if you go to the first one and it's not there, you can go to another copy and get it from there. There are problems with that. I mean, but they're all in the process of being figured out. I mean, actually having a RAME, which is a redundant array of memory servers, is quite fun. It's kind of like, it's the extension of distributed file systems, where you get to reuse all this local storage that is laying about, because disks are massive. And they put masses of gigabytes and terabytes in our local machines that we don't need. So let's reuse them as distributed file systems. When you create a cluster of 32 servers in a virtual pool, and you've got one machine that's got lots of memory, because it only has one VM on it, you might as well use all that spare memory for something else. And it's getting that right. Yeah.
Any more?
Awesome. Oh, last one.
Cool.
Has anyone talked about running it on different, different VM architectures, like KVM and Zen server?
Yeah, I mean, the KVM guys have a port of it running on KVM, but I don't know what the status of it is. They were one of the guys who were proponents of it and said, yes, we want it for the kernel merge. The kernel merge took years, by the way, because there was a lot of discussion internally. When Zen was not mainlined, there was a lot of discussion on LKML as to why should we mainline this when it only benefits a product that's not part of Linux. That was the discussion. Now that Zen's mainlined, this becomes more interesting. Yes, KVM is using it, but I don't know what the status is. I'm not sure how useful it would be for the others. It's not something that I think LXC would use that usefully. Potentially, but not. It's in the kernel anyway for that, so you don't really need a lot of work around it. The more interesting stuff is porting it to non-Linux operating systems, of which we have one, which is quite fun.
Windows?
No, Solaris. We have that one too.
What's happening with Windows? Like, not
Well, Hyper-V does it to a degree. I mean, the history back in the day, in case you're really interested, is Hyper-V is very Zen-like, because the Zen project was originally funded by Microsoft. This research project that created Zen was a Microsoft project. So there's no Zen code in Hyper-V, but there is Zen concepts in Hyper-V. And the Enlightenment kernel, which runs Hyper-V and runs Windows guests, is a para-virtual kernel. It's Microsoft is one of the few that actually does para-virtualization.
Quick, very last one.
Last question, yay!
So from a general community perspective, we've got no restrictions in terms of patents around the technology and licensing?
No, it's all mainline.
Mainline.
It's all mainline. Yeah. Now, just a quick plug. If you want to play with this stuff and you want to play with a mainline kernel, but you don't feel like building your own, Oracle Linux has a playground channel on publicyum.oracle.com where we actually build a mainline kernel and an upstream kernel every day. So if you want to really play with upstream and mainline, but you don't feel like building it yourself, go to Public Yum, subscribe to the Playground channel, and you can install a 3.7 kernel on Oracle Linux 6. And it has things like the latest Btrfs, the latest TMEM, the latest LXC is in there as well, which is quite fun. So we're building it because we are testing it, and we're now publishing it as well. Absolutely no support for that. Do not install this on your production Oracle boxes. No.
Okay,
Thanks,
I guess
guys.
we have to wrap it up here, and on behalf of...
Thank you.